This video is brought to you by the European Center for Virtual Reality in Brest, France. The purpose of this work is to obtain a controller for an agent that can reach a given goal in a virtual environment. For the virtual environment to approach the real world in complexity, events inside it should happen in real time. Its space should be three-dimensional and continuous, meaning that objects can move or rotate by any amount. The virtual world should function according to the familiar laws of physics so that objects can collide, fall or become occluded. Finally, the entities populating this environment should exhibit behaviors such as moving around, detecting predators and avoiding them. What we ask of our agent is to be adaptable in such a dynamic environment. To this end, we take inspiration from how humans and even some species of animals perform mental simulation for goal-oriented behavior. We refer to mental simulation as the ability to create alternative realities in one's mind. Research in cognitive science suggests that the same core brain network might be responsible for seemingly different abilities. More specifically, reliving past events, envisioning future actions, adopting the point of view of someone, and navigating in the environment may be closely related. Further research also suggests that the ability to create purely imaginary scenarios, also known as counterfactual thinking, could also emerge from the same mechanisms in the brain. The relatively few computational applications of mental simulation in literature provide an intuitive glimpse into the agent's decision-making process, through visualization. State-of-the-art agents use the mental simulation paradigm to generate alternative scenarios, versions of themselves or potential outcomes of their actions. Applications include, but are not limited to, robot resilience, imitation learning, cooperation and adaptive behavior with human users in the loop. However, despite the common mechanisms suggested by cognitive science, computational approaches to mental simulation use specific simulators for the task at hand. Therefore, our approach in this work consists in a generic agent architecture for mental simulation. To test the functionality of our architecture, we developed a simplified virtual replica of a predator-prey scenario found in nature. The obtained virtual environment maintains the aforementioned key properties required for realism. Put simply, the chosen scenario consists in a cat whose goal is to catch birds. While hunting, real cats generally employ a stealthy approach followed by a short rush before striking. The cat agent, Orphy, is controlled by our system, while the birds are autonomous and behave in an approximately circular pattern. However, to make it more difficult for Orphy, the birds are also able to detect the predator, in which case they change trajectory and flee, making them a very unlikely meal. By adding obstacles in the scene, through which the birds cannot see, our hope is that Orphy will find a way to use them to its advantage. We note that the sole mechanism for Orphy's decisions is its mental simulation capability. More specifically, no built-in strategy has been given to the system. Once placed in the environment, the cat will start about 20 parallel mental simulations, 4 of which are shown on the right using a visualization tool. For clarity, the top left mental simulation window shows only the cat's actions. In each imaginary scenario, the system will test a sequence of random actions, such as advance, turn left or right, and jump. These actions are continuous and depend on time. When a mental simulation leads the cat close enough to a bird to catch it, the imagined action sequence is synchronized with the real time and performed in the environment. Repeating the process, Orphy is able to find a way to catch its prey. But does it adapt to changing environment conditions? We have recorded the cat's trajectory over a period of time, the locations where it caught birds, while varying the obstacle shapes and the distance to which birds are able to see. Results show that Orphy does indeed change its behavior. This is most obvious when varying view distance for birds. At zero view distance, the cat's distance from the closest obstacle follows a fairly normal distribution, and most birds are caught in open ground. When increasing view distance to about the length between two obstacles, Orphy begins to walk closer to obstacles where the catch count also increases. Doubling view distance for the birds determines the cat's trajectory to further approach the obstacles, where the majority of birds are now caught. Also, changing the shapes of obstacles to cylinders bring a small but consistent change in the way Orphy catches birds. This shows that the agent using our architecture is able to adapt to both environmental and behavioral changes. The cat's behavior was also investigated in detail and four emerging strategies could be distinguished. In the case where the birds do not see, the cat simply chases and catches them. However, as it becomes harder to catch in open ground because birds flee on its sight, Orphy begins to hide and ambush its prey. A variant of ambushing happens with cylindrical obstacles where the cat hides for a while and then sprints, as the geometry of the environment makes hiding harder. Finally, and most interestingly, Orphy anticipates that its approach will make the bird change trajectory and uses this in the presence of an obstacle to create a blockade and catch the bird. Although behavior believability is subjective by nature and therefore hard to prove, one can argue that these emerging strategies resemble the behavior of the agent's natural counterpart in reality. Orphy the cat is a toy example of the Orpheus architecture and has its limitations. In this scenario, the cat does not learn from its mistakes, and continuously rediscovers strategies without memorizing them. Furthermore, discrepancies between reality and imagination are not currently minimized. Finally, its mental model of birds is specific and cannot be reused for other types of entities. However, Orpheus allows its models to be changed seamlessly. Therefore, the next step is to completely replace specific models with machine learning algorithms that automatically adapt the agent's imaginary world to new content. Our research has produced Orpheus, a generic agent architecture that uses mental simulation as the core decision-making process. Orpheus has also been applied in significantly different scenarios in which agents are required to make decisions in dynamic environments, with time constraints. Experiment results have shown that the agent using our architecture can adapt to environmental and behavioral changes. Finally, its behavior and emerging strategies resemble those of its natural counterpart in the real world, without prior knowledge of concepts such as hiding, ambushing or even representing a feline. Thank you for watching this video on our mental simulation-based agent. If you find our approach interesting, our agent source code is published on Bitbucket. This architecture, Orpheus, has also been made open source and can be freely used by anyone to build autonomous agents.